What is up, ladies and gentlemen? This is a video walkthrough of problem 6 on CS61B Spring 2022, the final. Let's get started. So in this problem, part A reads, suppose that we have a collection of functions, f of I, that take a single integer as argument, such that fi of n is big O of n for all I. Then we define the function g of n, which is equal to the absolute value of f1 of n plus absolute value of f2 of n, and so on up till the absolute value of fn of n. And the question is that is g of n omega of n squared? All right, so when we're kind of thinking about this problem, let's first maybe think about ways of defining fi of n. So when I approach problems like this, where there's yes, no possibilities, let me first try thinking of a counterexample. If I can't think of a counterexample, that maybe would hint that it's true. So in order to think of a counterexample to this, we would want to choose fi of n to be small so that g of n is small, and this bound isn't true. So just to kind of like relay my intuition, what I'm thinking here is that I'm trying to think of a counterexample, just maybe playing around, because I think thinking of counterexample might be easier than proving this is true. So to think of a counterexample, I want to find a g of n that is not omega of n squared, right? So I want to find a g of n that's smaller than n squared. So since g of n is defined with these fi of n's, maybe I could try to define fi of n to be small so that g of n is small, and then this bound isn't true, right? That's kind of the intuition we're going about here. So let's consider defining fi of n, and let's say I'm doing this for all I, where this is just equal to 1, right? So if fi of n is equal to 1, right, it kind of just runs in constant time, it takes constant work, this fi of n function, then what this implies is that g of n is going to be equal to n, right? More specifically, it would be equal to like 1 plus 1 plus 1, which is just n, right? So what we'll see here is that n, right, which is kind of the cost of g of n, is not omega of n squared. So we know that this is false, right? So we're kind of now debating between either of these two options here. And the reasoning why I'm going to choose this one right here is because we kind of made f of I of n arbitrarily small. Okay, and if you kind of think about it like that, it kind of makes sense that, hey, if I define f of I to be arbitrarily small, then this isn't true, right? So this one above, I wouldn't say it's the best answer for a couple of reasons. The first one is, this is kind of like it's kind of a vague statement that doesn't really have relevance to the problem that we're solving right now. Say I said that maybe this was like omega of 1, right? Notice that this would be true, right? Like if I changed this prompt to make this omega of 1 here, now this would be true. So even though like big O and omega are like different bounds, we can't say they're unrelated, so it's false. That doesn't really make any sense. All right. So yeah, let's move on to the next one. Okay, let's move on to part B. So part B states that if f of x is theta of g of x and f and g are both positive value functions, then f of x minus g of x is omega of 1. So this one is actually false, and maybe a quick way to see that is imagine if f of x is like 5x, and imagine if g of x is 4x, then what we can kind of see here is that f of x minus g of x, right, if we're looking at that, is going to be x, and x is not in constant time, right? X is linear time. So yeah, let's move on to part C. So part C states that if f and g are positive valued functions, and f of x is big O of g of x, then there is some constant k greater than 0, such that g of x over f of x is greater than or equal to k for all x bigger than some value, right? So let's first recall what it means for a function f of x to be big O of g of x. So let's kind of write that here. So recall then what we can say is that f of x is going to be less than or equal to, let's say, some constant m times g of x when x is bigger, or for all x bigger than some value. For all x bigger Okay, so this is just like the definition of what it means for f of x to be big O of g of x. It means that f of x is less than or equal to m times g of x, where m is just some constant, for all x bigger than some value, right? So this is what it means, and what this question is saying is that, is this also true, right? Can we maybe try to manipulate this expression to get it to look something like that? So let's take this expression here and see if we can manipulate it a little to look like what was in the prompt. So we know that this is true, right? So what I can say is that if I divide both sides by f of x, then I could say 1 is less than or equal to m times g of x over f of x. And now if I divide both sides by m, I could see that 1 over m is less than or equal to g of x over f of x. And then if I kind of just like rewrite this a bit, let's see that g of x over f of x must be greater than or equal to 1 over m. And then we know that m is a constant, right? So I can also say that this is maybe equal to some constant k, right? Let's say that, where k is just equal to 1 over m, right? So what we kind of did here is we rewrote what we knew was the definition of a big O bound, and we wrote it in a way such that this makes sense, right? So that's the justification for why this is actually true. All right. Let me just try to move this out of the way as we move on to part D. All right. So looking at part D, what it states is that what is the worst case running time of the call func d of L as a function of n? Assume that calls to P take constant time and that linked list refers to the Java class of that name. All right, so I think this problem looks a bit easy, but it's actually like mathematically a little more challenging than you might think on first glance. So we're gonna try to dive through the nuances here so it makes sense to us. All right, so if we're looking here, what we're doing is that we have n strings in L, right? Okay, we have n strings in L. So what we're going to do is that for every string, right, for every string x, we are going to iterate from j is equal to k up till n, and we're going to call get of j, okay? And then this is just some constant time function call, so we can just really ignore this and just kind of say that at every iteration of this for loop, all that we're really doing is calling l.getJ. All right, so let's kind of think about like how this is going to look. So we have this outer for loop here, okay? So what we'll kind of notice is that we have this value of k, and every time in this for loop, we increment k by 1. All right, so let's try to maybe draw this out. So let's say that we have, okay, so I'm going to create kind of two axes here. Okay, so this axis on this left-hand side is going to be the value of k. Okay, and it starts at 0, then 1, then 2, then 3, and then up till n, right? And you can also think about the value of k as kind of in respect to this outer for loop, right? So the next thing that I'm going to consider is the value of j, right? So the first time around, j will start at 0. Right? And then the second time around, j will start at 1, and so on. Okay? So now what I'm going to do is, for every value of k and for every value of j, I'm going to put how long l.getJ takes. Okay? So let's kind of see what I mean by that. So initially, when k is equal to 0, right, you can also maybe think about this row here as the first, like, for the first string in L, okay? So that's kind of corresponding to this row here, right? It's for the first string in L. In other words, when k is equal to 0. So when I call l.get of 0, notice that we have a linked list, right? So one thing to kind of notice here is that the get call for a linked list kind of takes us theta of j time, right? So imagine like if j is equal to like n, if we have like a linked list, we'll probably just kind of go in order, right? So you might say, hey, Soham, like, what if j is equal to like n minus 1? Maybe it'll make more sense to go in reverse order using that doubly linked list that we talked about. For simplicity, let's just assume that whenever we call get, every call to get just kind of iterates in order of the linked list and doesn't really go in reverse order, because we'll see it doesn't really matter asymptotically. Okay, so what my claim is that, or my assumption I'm going to make is that l.getJ takes us theta of j time, right? So if like j is equal to 0, it'll take us like basically constant time. If j is something like n over 2, it's going to take us n over 2 time because we have to traverse all of the links up till the n over 2 indexed node. Okay, so with that in mind, let's try filling in this little table I have here. So we call l.get0, and that'll take us, let's say, constant time. And then maybe when I call l.get1, then maybe it takes me, let's say, 2 time, and then 3, 4, 5, and so on. Okay? It doesn't really matter, like these off by 1 factors. So what we'll kind of notice here is that this is what kind of results when we are considering the first string in L or when k is equal to 0, right? So when k is equal to 1, notice here that we now start at j is equal to 1, right? So in essence, we're only going to have these terms here. More specifically, we're not going to have any term right here, right? The second iteration, right, of this outer for loop, we notice that k will get incremented to 1. So we kind of have these terms here. So if we're looking at the next time around, now k gets incremented to 3. So we'll have all the terms from 3 onwards, right? And what we'll kind of notice is that this pattern will continue, where the next iteration will start 1 later, right? We'll start at 4 this time. And then finally, if we're looking at like the 'nth iteration, then we'll have all the terms maybe up till n. Something like this, right? This is not, I'm going to say like there might be some off by one terms here, it may not be 100% correct, but the gist of what the runtime and the work that this function is doing is captured by this little table, okay? And if you guys are kind of confused what this table is, let me explain once more. So what this table is saying is that this left-hand side says for every value of k, right? And you can also think about this as that when k is equal to 0, we're considering the first string in L. When k is 1, we're considering the second string in L. When k is 2, we're considering like the third and so on, right? For every string in L, right, we issue a certain number of L.getJ calls. So if I do L.getJ when j is equal to 3, that takes me, let's say, 4 work, right? So this is the total amount of work that we do in the iteration when k is equal to 3 of this for loop. All right. So in order to find the total runtime of this function, I have to find what this sum is equal to. Okay. Oops, I didn't need to make it into an arrow. But yeah, the gist is I have to figure out what this sum is equal to here. All right. So that's kind of like the task at hand, is to say, hey, what's the value of this kind of triangle? Okay. So one thing that we can kind of note here is that this black triangle looks a little tricky, right? It kind of seems hard to find the sum of this. But what do we know the sum of here? One thing I want to claim is that we know the sum of this orange section right here, right? Asymptotically, the sum of this orange section is n squared. So let's, maybe for simplicity, let's just assume that this grid was fully filled, okay? Let's assume that we have these kind of missing terms here, and this grid was completely full. Okay? So if this grid was completely full, then one thing I kind of want to note is that we know that each of these rows asymptotically is equal to n squared. So the whole grid would be asymptotically on the order of n cubed, right? So we know one of these is n squared. So if we're kind of looking at the whole thing here, right? That's going to come out to n cubed asymptotically, right? Because we have n rows and each row takes n squared time. So now what I'm going to argue is that this black section here is at least half of the bigger grid. Okay, so what my claim is that this, let me try to clear some of this stuff out of the way. This black triangle is at least half of the bigger grid. So one way you can kind of see that is if you take this like black triangle and you kind of flip it along the diagonal here, notice it's going to be bigger than all of these terms, right? Or like a little bit bigger, right? Like if you're kind of taking this triangle here and you're kind of flipping that triangle, then notice here that 5 is bigger than 4. Maybe this 5 is bigger than the 1 that it'll get flipped to, and so on. So visually, hopefully it's clear to see that this black triangle must be at least half of the bigger grid. Though it's probably going to be like, it's probably going to be more than half of the bigger grid. And we know the size of the bigger grid is n cubed. So the black triangle, right, that implies the size of the black triangle is at least like n cubed over 2. And we know that dividing by 2 doesn't do anything asymptotically. So what we can kind of say here is that the size of that black triangle, right, this same black triangle is n cubed asymptotically, okay? So I'm going to go ahead and put n cubed here. Another way of actually seeing this that's pretty cool is that the amount of work that we're doing in this black triangle turns out to be the sum from I is equal to 1 to up to n of I squared. Okay, it's actually the sum of the first n squares is the amount of work we're doing in this black triangle. So one way of seeing that is we're doing 1 plus 2 squared plus 3 squared plus 4 squared plus 5 squared and so on, right? So the black triangle is actually equal to this sum right here. So if you guys are familiar with the sum, you guys might recall that this actually runs at n cubed time. If you guys aren't familiar with it, I actually didn't know the value of this sum. I feel like it's still possible to derive what this sum is just by kind of using this intuition of the grid. Yeah, so that was n cubed. Hopefully you guys thought it was kind of fun diving into the nuances there. So looking at part E reads, what is the worst case running time of the call func E of n as a function of n? Assume that calls to P take constant time, and they give us a hint that we presented an algorithm in class that behaves like this when studying heaps. Okay, so what this hint is saying is that this algorithm is like a bottom-up heapification. Okay, so let's recall like what bottom-up heapification is. So imagine that we have some sort of heap. Okay, so let's say that we have like some heap here. Okay, so when we have this heap, and let's say that this heap initially isn't a heap, right? Let's say like there's just random values here. And let's say I'm trying to make this into a max heap, right? So when I run, or let's say I'm trying to make it into a min heap, a max heap doesn't really matter, right? So when I'm doing bottom-up heapification, what I do is I look at the elements right here, and in reverse order, I call bubble down, right? So just to recap, I go through these elements in reverse order and I call bubble down. Right? That's the process of like bottom-up heapification. And we don't really have to call it on the bottom row because you don't have to bubble down a leaf node. It's not going to change, right? So one thing to kind of think about here is maybe let's give these guys indices, okay? So I'm going to say that this is like, let's say 1, 2, 3, and let's say so on. And let's say this is like the halfway point in our heap. So let's say this is n over 2, right? And let's say like this is n over 2 plus 1 up till n. So these aren't like exact like values, but one thing to kind of notice here is that when we're looking at the size of this heap, half the elements will be in this triangle here, and maybe around half will be on the bottom row here, right? Assuming that it's like fully filled on the bottom row, okay? But what we want to know is that like this value here, we could say that this node's maybe the n over 2 or like the halfway point in all of the nodes, right? So since we're iterating in reverse order, we're starting at the n over 2 node and then going smaller by 1. So that actually is exactly what this for loop here is doing, right? We're starting at the n over 2 node, and then we're kind of going in reverse order until we get to this root, right? So what we can kind of see here is that this for loop matches pretty closely with our calls to bubble down, right? So now let's kind of consider this inside for loop. So this inside for loop, I'm going to claim is kind of the worst case behavior of one call to bubble down. So this is kind of like the worst case behavior of one call to bubble down. So let's see like what I mean by that. So suppose that I call bubble down from this 2 node, okay? So when I call bubble down from any node, I swap it with its like parent, right? So if I'm swapping it, okay, when I call bubble down, I take that back. I swap it with its child, right? So this node here has 2 children, right? Let's say that I decide to swap it with, I'm going to change these values. let's say I decide to swap these two nodes here, right? Let's say that like, let's say this is 1 initially, and then, yeah, let's say we do this swap, okay? So after doing the swap, what you can kind of notice is that the index of the 10 element changed from 2 to 4. You guys see that? Like I went from 2 to 4, and that's how the index of the 10 element changed, right? Okay, so then now if I'm considering like, hey, let me do this one more time. If I do another swap where I'm going maybe from 4 to 7, like if I do another swap here, then the index of the 10 element would become 7, right? So what we're kind of noticing is that this loop keeps going, right? It starts at 2, then we double it to 4, then maybe roughly double it to 7. And that's exactly what this process here is doing, right? K starts off as I, and then we keep doubling K, right, as we go through this for loop until K becomes greater than N. So that's precisely what we're kind of doing when we bubble down. If we consider that K is this index here, then every time I bubble down, I do like one sort of swap, then I'm multiplying K by 2, right? 2 to 4 is multiplied by 2, and then 4 to 7. So you say, hey, Soham, like, what if we always choose the left one as we kind of bubble down? So we're still like roughly doubling by 2, so it doesn't really change the runtime there. All right. So yeah, kind of coming back here, this process is just kind of a simplified way of thinking of the runtime of bottom-up heapification, right? So we know the runtime of bottom-up heapification is theta of n, and this was from lecture. So the runtime of this problem is just theta of n, because it's doing the exact same thing as bottom-up heapification. All right, so yeah, this is the last one here for this problem. And it says, what is the worst case running time of the call to func f of n as a function of n? So what I'm going to see here is that func f calls f2, and f2 calls f3. So let's just first figure out what the runtime of f3 is in terms of k. So if we're kind of considering f3 here, let's maybe draw its recursive tree, right? So we have some k here, then it kind of issues 2 calls to k minus 1, right? Which then branches again to 4 calls of k minus 2 and so on, right? So what we'll kind of notice if we're looking at like the recursive tree that develops whenever we call func f of 3 with some starting value of k is that every level kind of doubles the amount of nodes that it has, right? So if we're kind of considering like maybe the work per level, we can see that each one of these nodes does a constant amount of work. So if we're trying to find the work per level here, right? This is work per level. Then if we're looking at this starting row, it's like 1 plus 2, right? Plus 4, plus 8, and so on, up till, well, we can kind of think that the height of this tree is k, and we're kind of doubling each time. So you can think to yourself that the number of nodes on the bottom layer is going to be k. So the work that this bottom layer does is 2 to the k, right? So what my first claim is that func f3 is theta of 2 to the k, right? All right, so let's go to f2. So what f2 does is that it takes a value of n and a value of k. So we can kind of see here that k starts off at 0. So if I'm looking at like f2, let's maybe draw out like a similar recursive tree. So initially we start off with n and 0, right? Then what we're going to do is we're going to have n over 2 and 1. Then we'll have n over 4 and 2, right? And so on. We'll keep dividing n by 2. until we hit 1, and then maybe some value here that's, let's say, currently unknown, right? So if we're kind of considering the height, what's the height of this tree? So the height of this tree is actually going to be equal to log of n, because we keep dividing n by 2, right? So the height of this tree here is log of n, and we can kind of notice that this value is going to be equal to the height of the tree. So the height here is, right, log of n. So we're going to say that this last term is log of n because every time I go down one level, I increase k by 1. So we can say at the bottom level, the value of k is going to be log of n, right? So now let's kind of put it together here. So after calling func f2, the value of k that we're going to put into this recursive call is going to be log 2 of n. And then we know that after calling func f3, it takes us theta of 2 to the k time. So if k is equal to log 2 of n, that means the runtime of func f, let's say func f, is going to take theta of 2 to the log 2 of n. So the reason is that func f, all it does is that, okay, let me actually clarify. So func f, what it does is that it first calls f2, and then at the end of calling f2, it'll then call f3, right? So this is a little more complicated. Let me clarify. So func f is going to be kind of composed into 2 parts. Okay, we'll call func of f2, and then func of f2 then calls func of f3. Okay, so if we're looking at the runtime here, the runtime of func of f2 takes us log n time, right? Because we have log n nodes in this tree. And then after func f2 terminates, right, then we call func of f3. Func of m3 takes 2 to the k. Well, what is the value of k? K is 2 to the log 2 of n. So this actually simplifies 2 to the log 2 of n. There's like a neat log trick that simplifies this to n. So func f will spend log n time in the recursive calls of f2. Then it'll spend n time doing f3. So the total runtime of func f is kind of the sum here of log n plus n, and asymptotically n dominates. So what we can say is that the runtime of func f is going to be theta of n. And yeah, that's all for this problem. I hope you guys enjoyed this video walkthrough.